Warm round of applause and go ahead and get started.
Thank you, everyone. Hello, my name is Mike Rash. Thanks for the introduction, Brian. So this is my third ShmooCon talk. I'd like to thank the ShmooCon organizers for seeing fit to have me back. The first talk was back in 2006, and the topic back then was also single packet authorization, but things have come a long way in the SPA world since that time. So I find that usually it's a good idea to give a little bit of an introduction to where SPA came from. It kind of grew up out of the port knocking world, but it is, I would say, quite different than port knocking generally. I found also in previous talks that it's kind of difficult to kind of leave enough time to give a really lengthy demonstration of the technology. So I'm going to try to fix that in this talk. There's a lengthy demo of integrating FWNOP with Amazon's AWS cloud service. From there, we'll try to hint at some generalized points for integration for other cloud architectures. The FWNOP 2.5 release, I was trying to finish it by ShmooCon here, couldn't quite get it done, but it's very close. This release is going to finally introduce HMAC SHA-256 support for SPA packet authentication, and talk a little bit about where SPA is headed from here. So in both the port knocking and the SPA worlds, we kind of assert that there's value in the idea of concealing a service behind a lightweight layer that is passively collecting information to be authenticated. But port knocking and SPA are quite different technologies. Neither one is designed to protect against client-side vulnerabilities. They're designed typically to protect against potential server-side vulnerabilities, and also to make services, make it infeasible to scan for services. So really what both port knocking and SPA are about is trying to make sure that services that may be vulnerable and may also include a lot more complicated code than the PK or the SPA implementations, we're trying to make sure that those services are something that you just cannot even know what to target because you cannot even scan for them. So typically we're referring to TCP-based services here, of course. UDP sockets are not required to respond with any data whatsoever, although of course many UDP servers do actually respond. So even though neither port knocking nor SPA are designed to protect against server-side or client-side vulnerabilities, there's certainly no shortage of server-side vulnerabilities. I chose these 4 specific examples because they're all recent, so within the last 2 months or so. And if I'm asked, if I were to take the trade-off of trying to deploy an SPA protective layer against services that may have problems like the ones listed here, yeah, I'll take that trade-off. My reaction to the third one on the list here, the nice, very well implemented Shodan service for regularly scanning the internet, looking for all sorts of services to be able to connect to. My reaction to seeing things like this is, let's just not connect things to the internet that shouldn't be connected. PLCs that are connected into water treatment plants and connected to the power grid, probably not the best things to connect to the internet. I know it's not that simplistic, of course. People find it very useful to be able to connect to things over the network. But firewalls are all over the place too. Let's use them. So the typical port knocking, and by the way, please feel free to interrupt me at any time if you have questions. Prefer this to be a little bit more interactive, so speak up. Both port knocking and SPA have a similar workflow where you have a system that is leveraging a firewall layer of some kind, IP tables or IPFW or something, and it is passively collecting data from a user that is in possession of a port knocking or SPA client. And that client is producing a set of information which is then passively collected by the PK or the SPA server side, and then temporarily reconfiguring the firewall for access to whatever service is being requested. in many cases, people use it to protect SSH daemons. FWNOP started in the port knocking world. It was, at the time, it was the first implementation that combined port knocking with passive OS fingerprinting. But things have come a long way since then, and it's designed today to try to retain the benefits of port knocking, namely the default drop packet filtering stance for protected service, but at the same time solve limitations that port knocking implementations typically have, such as it's difficult to protect against replay attacks typically. You can, if you're requiring a sequence of connections to closed ports, as in most port knocking implementations do, it's very easy to DOS the port knocking server side if you're an attacker just by spoofing an additional packet into the port knocking stream, thereby convincing the server that you don't really know the proper sequence and thereby denying access to the person who's trying to gain it. SBA is designed to solve those limitations. So there are many different port knocking implementations, and there are a few SBA implementations. And the particular design goals that if you're looking at an SBA implementation, the particular design goals that guide the development of that project are probably going to influence whether or not you are willing to run that particular piece of software. So it's probably a good idea for me to talk a little bit about the design of the FWNOP project. So we talked about passive collection of authentication data. Currently that's done with libpcap, although I have a star there because that's going to be changing in in a future release of FWNOP with some different modes of acquiring packet data. It supports both symmetric and asymmetric ciphers, so Rindal for the symmetric key encryption, and it supports GPG for asymmetric encryption. Encrypted, of course, and non-replayable packets. And when I say encrypted, because FWNOP uses UDP, by default it sends a UDP packet over port 62201. Of course, the server side is never acknowledging anything whatsoever. The IP address that you want the FWNOP daemon to allow through the firewall is encrypted within the SBA packet payload. That's a very important point because any SBA implementation that does not encrypt the IP within a payload, of whether or not that payload exists somewhere in network or transport layer headers or in the application layer of whatever protocol you're using, if it doesn't encrypt the IP address within the payload, then that SBA implementation is potentially subject to a man-in-the-middle attack, where an attacker can intercept the SBA packet, change the IP address in the network layer header, and retransmit, and thereby gain access for whatever IP they chose to put in that header. So it's important, if you're looking at maintaining the security of this architecture, to encrypt the IP within the SBA payload. FWNOP today is written in C. I'd like to thank Damian Stewart for doing a port of the old Perl FWNOP implementation to the C code. Currently, Damian and I maintain the code. It's an open source project, of course. So I'd like to report that in the C implementation, FWNOP is now portable to embedded operating systems. At one point, I had purchased a few years ago one of those little Linksys WRT54G routers that can be reflashed with the OpenWRT Linux distribution. And at that time, FWNOP was written in Perl, and so I was trying to get the Perl daemon to run on OpenWRT in that little router, and it didn't work so well because it's a very small, it doesn't have very much CPU or memory horsepower. In the C rewrite of FWNOP, it now can run on that same little Linksys router because it's a very lightweight implementation. We also wanted the server to be portable to different firewall architectures and router ACL languages. Today, currently, it supports 3 firewalls, so IP tables on Linux, IPFW on FreeBSD and Mac OS X, and also the PF firewall on OpenBSD. At the same time, we wanted the client to be portable to pretty much everything from the Cygwin to the iPhone. And there are lots of competing environments where people don't have privileged access to their local operating system. We did not want to require that the SBA protocol manipulate packet headers via a raw socket or something like that. We wanted to just allow unprivileged users to be able to create SBA packets without requiring any specialized access. And finally, we wanted to minimize library dependencies. That's the hint that I made earlier about not necessarily linking against libpcap, and we'll talk a little bit more about that later. Okay, so just a couple more slides on this. There are some corollaries to the FWNOP design. In this case, this slide is to show that from an attacker's perspective, not everything is always, things aren't always as they seem. In this case, what we have here is a client, an SBA client. This user of FWNOP, let's say, is trying to gain access to a service that's protected on network B, and they're coming from network A. But remember that the FWNOP encrypts the IP address that is to be allowed within the SBA payload, which means that the actual source IP of the SBA packet itself is totally meaningless. So it can be spoofed. In addition, the sniffer, the SBA sniffer, does not have to acquire packet data. It doesn't even have to have an IP address assigned to the interface where it's sniffing, which means that the destination IP also of the SBA packet is totally meaningless. So a user, the only requirement is that the sniffer is on the routing path of an SBA packet as it traverses the network, which means that just for sake of argument here, assuming the routing would actually work, you could make it look like an IP owned by Google is communicating with an IP owned by Yahoo, and you're sending this SBA data across the wire, and that results in this totally unrelated packet sniffer over here reconfiguring itself to allow you to access SSH from this particular network. Depending upon where an attacker might be placed within the network, what would they see? They would see a blob of base64 encoded data going from an IP owned by Google to an IP owned by Yahoo, and they might say, oh, but there must be an SBA sniffer running on Yahoo's network over here. Let me go attack them. So if you want a tutorial on single packet authorization, this one's fairly comprehensive. It's up on the cipher9.org website. It's currently written against FWNOP 2.0.3, and it will be updated once the new HMAC SHA-256 support is added. Okay, any questions up to now? Yes? So the question was, does the IP header need to be encrypted so it can't be spoofed? So the IP that is to be allowed through the firewall is encrypted within a UDP packet payload. So there are other SBA implementations that do manipulate raw packet headers and encode information within those headers. The FWNOP implementation does not do that. So when I say spoof the IP, I just mean that the FWNOP client, if you have administrator level access to your local operating system, you can have it create an SBA payload as a part of a UDP packet, but it can also at the same time spoof the source address. On the server side, the FWNOP daemon doesn't care about the source IP of the network layer header. So it doesn't use that in the authentication process at all, or decryption process. So it's just sniffing that blob of binary or base64 encoded data, and if it properly decrypts, it will take the IP that's to be allowed from that decrypted payload.
How does the network sniffer identify which packets need to be inspected?
So the question was, how does the sniffer identify which packets need to be inspected? So by default, it uses a Berkeley PCAP filtering statement to only look at packets that have a UDP packets to a destination port 62201, but you can customize that however you want. There is the FWNOP client supports, if you want to send SBA packets over ICMP, you can have the sniffer sniff ICMP packets. If you wanted to restrict the daemon to only sniff from particular network segments. You could also express that as a Berkeley packet filter statement. It all comes down to what your Berkeley packet filter statement looks like. Any other questions? Okay, so SBA and the Amazon cloud. Before moving to the demo, I need to set the stage just a little bit. So this is a snippet of the Amazon user agreement. And they explicitly say in their user agreement that you are responsible to protect your data, and that may involve the usage of encryption technology to do that. So I kind of said, okay, well, it seems like maybe FWNOP kind of functions in that way, and it's a little bit different, a different take perhaps on protection. But I decided to see if it would work, and it seemed to me, based upon my read of this, that it was compatible with their user agreement. Not all user agreements that people enter into with cloud providers might, they might look different. But out of an abundance of caution, I did ask the Amazon security team what they thought, and I don't want to imply that they are endorsing that technology, but at least they said that it doesn't appear that SBA is incompatible with this user agreement. So it seems that there's coverage there. Okay, so Amazon Virtual Private Networks, or actually Virtual Private Clouds is what VPC stands for. We're going to simulate we're going to have a home or corporate network here. The Amazon VPC network is a private cloud that you instantiate through the Amazon Management Console, and you can create individual host virtual machines within that cloud from a selection of images that Amazon provides, or you can roll your own. And you can access machines in that virtual private cloud by using Amazon's Elastic IP service, which are externally internet routable IPs that you can run whatever service you like down into these virtual machines running within your cloud. So kind of need a use case perhaps. Early last year, there was a serious vulnerability announced in Microsoft's RDP service used to manage Windows systems. I checked a few weeks ago, and Metasploit today doesn't, at least as far as I know, doesn't yet have a remote execution module for this particular vulnerability, but they do have a DOS module, and it stands to reason that someone out there may be able to remotely exploit and get code execution for this vulnerability. Maybe not, who knows, it's unknown, I suppose, but at the very minimum, it is a serious vulnerability. So for a time, before this vulnerability was discovered and announced to Microsoft, cloud provider images were vulnerable to this, in which case, exposing them to the internet. I know that a lot of people will choose to hide RDP services behind a VPN service like OpenVPN. That's fine. This is an additional protective layer that could be deployed in conjunction with that too, so they're not mutually exclusive. But there's just one problem, which is that FWNOP does not support a Windows firewall. So what I was trying to figure out was whether or not I could provide an SBA protective layer for an RDP service running on a different operating system, not even supported by FWNOP. So the answer to the question is yes, it does support this scenario, and what we have depicted here is, so the demonstration is going to create a VPC network within Amazon's cloud. I'm going to instantiate two systems within that cloud, an Ubuntu system where the FWNOP daemon is going to run, and a Windows instance where RDP is listening. Through the usage of both SNAT and DNAT, which the FWNOP daemon supports, I'm going to transform the Ubuntu host into essentially an internal gateway inside the VPC network for other services. So this has a couple of consequences. I will be able to access RDP. I will have an SBA authenticated connection to RDP through the Ubuntu host through a single Elastic IP. The Elastic IP, I don't even need an Elastic IP assigned to the Windows machine, and even the Windows machine doesn't even need to have a default route out to the internet, because all it's going to see is what looks like an incoming connection from the Ubuntu host, whereas the actual source of that connection was out on the internet. So I have access to any internal system, any internal service through the Ubuntu host through a single Amazon Elastic IP. Simultaneously, I'm going to simulate a scanner system on this red network here that's going to be scanning the Elastic IP to see what it can actually see from a services perspective. A note on configuration. So there are two configuration files that are important to FWNOP on the daemon side, that is. This FWNOP-d.conf file defines some globally applicable configuration options. The gentleman over there asked about how it inspects packet data, how it selects what packets to inspect. In this case, the PCAP filter is set to UDP port 40,001. I'm just using that as to be different than the default. And then the access.conf file defines a set of stanzas where you define decryption keys. Remember, the FWNOP daemon has to be able to decrypt the incoming data in order to verify certain properties about it. And in this case, we're going to be using the force NAT mode, so we're going to also access the SSH daemon running on the Ubuntu host, and everything is going to go at the same time through port 80. So I'll explain a little bit more about that in a moment. Okay, this is a video demo. As you can tell, there's a lot of moving parts, kind of complex, but in defense of this, instead of doing it live, FWNOP is open source, free software. The configuration I just shown is exactly what I've used to make this work. Anyone in this audience can reproduce precisely what I'm doing here. So if you have any trouble with that, just email me and I'll walk you through it if it doesn't appear to work. Any questions before I continue? Okay, so I'm going to narrate here. Okay, so this is the Amazon Management Console, and I'm logged in as me, as you can see. There's one VPC network defined. There is one Elastic IP defined, which is that externally routable address. There's one security group defined, which defines an Amazon-specific ACL policy for incoming data. And there are two EC2 instances deployed in my VPC network. So if I examine what instances are actually running, this first one is an EC2 instance, which is tied to this particular Elastic IP. That's the IP that's internet routable, and if I bring that up in my web browser, I'm also running a copy of my website on that IP. This isn't live right now, so you can't go connect to it right now, but anyway. It is an Ubuntu 12.4 system that's one of the Amazon standard AMIs, and it also has non-routable IP 10.0.0.12 within the VPC network. Switching to the next EC2 instance, this is a Windows host with address 10.0.0.223. It's a Windows 2008 server, and it does not have an Elastic IP assigned. It cannot be directly addressed from the internet without going through special means. Flipping back to the VPC configuration, taking a look at the security group that's defined. This is the Amazon border ACL for incoming, that defines what kinds of protocols will be allowed into the VPC deployment. It's very restrictive. It only allows two things. One is HTTP on port 80 and UDP port 40,001, which is where we're going to send the SPA packets. And for emphasis, there's one Elastic IP again defined. Which is where that website is running. Okay, now flipping over to 4 consoles that are running. So the console in the top left with hostname Rohan is, this represents the scanning system. It has its own IP out on the internet that is independent of the other 3 windows. All of the other three windows are where we're going to be running the SPA packets from, as well as the SSH connections and the RDP connections. Let's first scan port 40,001, and as you can see, this bears a little bit of additional explanation here. So note that Nmap has reported that the state of that service is either open or filtered. That's the standard output that you get from Nmap when it doesn't get any response back. So because UDP services aren't required to respond ever, necessarily, Nmap can't tell the difference between an open service that may be bound to that port or one that is actually filtered. Now, one thing to note is that the Amazon ACL, which I showed you earlier, allows incoming data to port 40,001. So you might have expected to receive, let's say, an ICMP port unreachable message if there were no service bound to that socket on the Ubuntu host inside. But I'm also running IP tables on that host with a default drop packet filtering stance, except for port 80. So the point of that is to show that there are two firewalls at play here. One is the Amazon border ACL, and the second is IP tables running on the internal Ubuntu host. And of course, no acknowledgement was ever sent by the FWNOP daemon because it's just a packet sniffer. So Nmap can't see that there's anything there to communicate with. So now let's run in a watch window. Nmap scans consistently for port 80, port 22, and port 3389. This is our scanning system. Remember that it has its own IP out on the internet independent of the other three windows. So I'm also going to launch the scanning system from the actual machine where I'm going to run all the SPA packets from as well, also within a watch window. So as you can see, Nmap's reporting that port 22 and 3389 are filtered. That's because the Amazon border control itself doesn't allow those communications to come through. Port 80 is open. It's running with version detection. Nmap's able to tell that it's Apache version 2.2.22. And the same thing appears from the system where we're going to be running the SPA packets from. So remember that all three of these windows represent where the SPA packets come from, and the scanning that I'm doing from here as well shows the same thing right now that the other scanner is able to show. Okay, so here I'm looking at this SSH access script. What this is going to do is going to launch the FWNOP client. We're telling it that we want access to port 80. Remember, the port 80 is already open. It's running a web server. We're going to send the SPA packet over port 40,001, and then we're going to send it to that elastic IP address assigned through Amazon's network. And then we're going to launch, after sending the SPA packet across the wire, we're going to launch the SSH client over port 80 to gain access to that Ubuntu host. So I type in my encryption key, run SSH, and now I have access through port 80 to the Amazon EC2 Ubuntu instance. So here what I'm showing is, at the same time, remember that we're still scanning from that same client-side system, and it's reporting that port 80 now is actually running an SSH daemon, whereas everyone else, represented by the external scanner here, can only ever see HTTP. This is the FWNOP daemon in firewall list mode that shows all of the rules that it adds to the FWNOP chains. There's a question. Yes?
Maybe I just missed the config. I'm just trying to remember in the beginning, where did you have the translation from 80 down to SSH? I remember before that 40,001 and all that.
Yeah, so the question is, where is the translation configuration? And the answer here, let me flip over to... So it's right here. It's this force NAT mode. So what this is saying is, I want to force for any SPA packet that was decrypted with this particular key, I want to force whatever connection is incoming from the IP in the SPA payload, force that to be NATed to 10.0.0.12, that's the internal IP of the Ubuntu host on same system, and NAT that transparently to port 22. So any incoming connection to port 80 is going to be automatically NATed into port 22 on the same system.
That makes a little more sense. The RDP is where I guess I'm missing.
Yeah, understood, yeah. So the RDP stuff, I don't actually have any specialized access.conf directives required to make this work. That all happens, and this is maybe something I should update in the FW.NOP configuration code, but this happens through this translation stuff over here in fw.d.conf. That's something that should be updated. Yes?
The key in the access.conf file, is that hashed? Can you show us plain text to us here for illustration?
So that's a great question. So the question is, are these keys hashed? In this illustration, the answer is no. That's changing in the HMAC SHA-256 support coming up. So actually, they're just going to be base 64 encoded, but the FW.NOP daemon has to be able to decrypt data. So it has to have access to the actual encryption keys themselves. And I mean, there could be an architecture where you could, let's say, start the FW.NOP daemon and then communicate it via like a Unix domain socket or something, and so you don't ever actually have the keys on disk. But then you run into issues where if the system goes down and reboots, then it can't, if you're not there sitting there live, you can't communicate the keys to it. So there's a lot of technicalities for key management, always is a headache. So the main point is that it has to be able to decrypt the SPA packets, so these are in the clear.
I just have one question. What
Yes.
kind of overhead is there because for like the larger files, I'm wondering, is there a significant hit or is it trivial?
So the question is there significant overhead for FW.NOP daemon operations, basically? So it's this. I would say in a word, no, because and actually I have some material on this a little bit later. FW.NOP is quite lightweight. I mean, you can define a large set of encryption keys, and I mean the encryption operations themselves are very fast, particularly on the Reindahl side. So in general, the answer is no. It's pretty lightweight. Yes. Yeah, so you could define a separate SPA stanza for each one of those. So it would support, even in the current way that it's written, you would be able to define enough stanzas to access pretty much arbitrary internal systems. Okay, so I'll continue with the demo here. So we've shown that we still have access. Oh, and by the way, note that the accept rules for the incoming connection for SSH have been deleted, but my connection is still open into the Amazon Ubuntu instance. That's because I'm using the connection tracking mechanism in IP tables to keep that connection open. Now, let's switch over to the RDP example. In this case, I'm going to launch the FW.NOP client again over port 40,001, and I'm going to say that again, I'm going to do this through port 80. I'm going to say now that I want to NAT. This is where you can say on the command line what other system you want access to. So this is client defined. I want access to 10.0.0.223 over port 3389, and then I'm going to launch. Then I'm going to launch the rdesktop command here over port 80. So letting that continue, I type in my SPA encryption key and launch rdesktop. And now I have access to the Windows instance through the Ubuntu instance. And I can log in as administrator. And note that here are my two scanners. Again, the normal scanner out on the internet always ever sees Apache. And the other scanner where I launched the SPA packet from currently says that port 80 is filtered. I don't know if that's because Windows 2008 has trouble accepting multiple incoming connections from the same IP. I'm not sure quite what's going on there. And then now that the accept rules have been deleted, the service switches back, even from the SPA packet system's perspective, back to an Apache web server. But again, the R desktop RDP connection is still open because it's using the IP tables connection tracking code to keep that connection open. So I have both the SSH connection and the RDP connection open still, even though there are no new connections being allowed. Okay, so let's now switch over to seeing a replay attack. In this case, I'm going to run FWNOP in verbose mode and collect its output via script. This little Perl invocation thing is just so you can't see what IP address I'm coming from on the outside. And I'm going to now, when I collect that output, I'll be able to replay that against the FWNOP daemon. So first, I'm going to send a new SPA packet in verbose mode, which means I'll have access to port 80 to SSH in this case. But remember, I'm collecting in verbose mode the client's output, which means I can see the exact packet data that it puts within the UDP payload. So I have access to SSH once again. The scanning system from the SPA system's perspective switches back to an open SSH daemon on port 80, and there's my accept rule. Which will be deleted. And so now I'm going to exit out of that new SSH connection. Note down in the bottom right, I still have my original one open. The scanner says it's switched back to an Apache web server, which is, of course, running in user space the whole time. And now I'm looking at the output of the client. So now here's the SPA packet data itself. I'm going to echo that through a Netcat UDP socket to the Elastic IP address. So this constitutes a real replay attack where an attacker that's able to sniff the original SPA packet is now replaying it against Amazon's network. I've sent it over the UDP socket, and no new access has been allowed because it is able to detect that it is a replay attack. And it also generates a log of that, which is shown here at the end. Okay, that concludes the demo. I'd like to switch over to the SPA cloud discussion. Any questions before I continue? Okay. So a few key points I think deserve to be mentioned. We did not have any special integration with the Amazon border control firewall. You know, everything that you saw was completely compatible with how Amazon builds their own filtering infrastructure, at least as far as SPA is concerned. That includes running SSH over port 80, RDP over port 80, and SPA packets over port UDP 40,001. So they're not implementing, at least as far as those protocols are concerned, any special filtering within their border. We had access to essentially any internal VPC instance through this Ubuntu host, which is effectively acting as its own gateway inside Amazon's virtual private cloud. And at the same time, I wrote a blog post a couple years ago talking about ghost services. So, you know, SSH daemons, RDP daemons, whatever other services you want are accessible because IP tables is able to manage the translation rules to access those services out from underneath user space. IP tables, of course, is running within the kernel. So even though Apache is up here in user space and accepting incoming connections for port 80, those incoming connections can be granularly modified by IP tables because it's running within the kernel at a layer, of course, where Apache has no opportunity to, to see how it's doing those manipulations. So can we go a little bit further and generalize this to other cloud computing environments? So some additional observations. Amazon's Amazon's implementation gives you as a user quite a lot of freedom. So you can instantiate full virtual instances, you can control what software is installed, you can install new software, you can manipulate firewall rules, you can run packet sniffers, whatever you want to do. And everything we've shown here is a defensive technology. It's not designed to somehow subvert what Amazon is doing with respect to billing or anything else. Simultaneously, there's no apparent filtering, specialized filtering within Amazon's border control. That doesn't have to be the case. You could imagine a cloud provider that actually would implement more restrictive filtering, like running a web application firewall or putting an IPS in place that doesn't allow certain kinds of packets to traverse their network. But Amazon doesn't appear to do that, at least with respect to things that we just saw. This translates to a good model for them. I mean, this gives us as users a lot of freedom, which means that things like SBA integration become easy. In the cloud terminology world, that's known as they are an infrastructure as a service provider. And it is my belief that to the extent that other infrastructure as a service providers, to the extent that they emulate how Amazon, the model that Amazon has, SBA would also be compatible with those other providers. Some may implement more restrictive border filtering capabilities. That's fine, and we don't necessarily need to be able to, or they might implement things like they might have strict controls between what VMs that you instantiate can communicate with what other VMs in your own cloud, perhaps. I don't know of a provider that does that, but it seems they could do that if they wanted to. And so we don't necessarily need to be able to have that NAT gateway capability. But in general, I would say that there is some level of integration possibility with SBA and other cloud provider networks. There are about 129 cloud providers listed right now on this Wikipedia page. Specialized providers such as, let's say, Dropbox and things like that are not listed in this list. And I think what they're trying to convey here, this is a listing of more of the infrastructure level, infrastructure as a service provider sort of deployments. So there's a lot of opportunity for the integration of this with those kinds of providers. There are other cloud architectures too that are somewhat interesting. If you as an organization have significant resources and you've purchased, let's say, a cluster of computers that you then build your own private cloud out of or layer on top of, SBA is likely compatible in two ways, where you can use it as you normally would with any bare metal operating system, and then you could also use it within the virtualization layer where you have OSs that are instantiated within the cloud. And that is following along along the lines of Amazon. Additionally, there are hybrid architectures where you have a private cloud deployment that interfaces with a public cloud component. And even though we didn't demonstrate in this talk the ability to send SBA packets out of Amazon's network to then authenticate to externally addressable internet services, that certainly works, which means that you could have bidirectional SBA authentication working between your public and private cloud components. So this flowchart is designed to make it easy to answer the question, to what extent is SBA, can it be integrated with an infrastructure as a service model, cloud provider model? And you can see that the first and kind of the most important requirement is that you can run full OS images, because this is what allows you to install your own software, manipulate firewall rules, and that sort of thing. If the answer to that question is no, then they're probably not really an infrastructure as a service provider, and it's also probably a lot harder to get SBA to be integrated in such a network. Then from there, if you do, however, have access to run your own OS images, then things get to be a little bit more clear. Then you can do things like test whether or not administrative protocols are actually allowed through their border control. Do they allow SSH at all? Do they allow RDP or some other VPN service? And then you can ask whether or not you can get SBA packets through the border control too, because that's a relatively customized, specialized protocol that's not, that doesn't follow along the model of most, certainly not administrative protocols like SSH or those sorts of things. If you get through all of those gates, then at some point, you can say that you've got some level of compatibility with SBA in those kinds of networks. Any questions? Yes?
Have you had any issues with NIDSs, you know, say, you know, blocking something or?
Yeah, so the question is, have there been any issues with network intrusion detection systems or prevention systems? Not on Amazon's cloud, for sure. You know, they don't seem to really care. I mean, they really allow you a lot of freedom. I have not, subject to simply the ports and protocols filtering that they do in their border ACL, I don't know that they're doing anything beyond that. You could, however, deploy an IDS in such a way, or an IPS in such a way that, I should say IPS in this case because it's a single UDP packet. You could deploy an IPS in such a way that it could potentially filter incoming FW-NOT packets. I wrote a brief article for a Hacking 9 magazine a few years ago about, so there are some steps that FW-NOT takes to make it a little bit more difficult to write a signature to detect FW-NOT packets. And so the question would be, can you write a signature or some other descriptor within your IPS infrastructure to reliably detect FW-NOT communications and differentiate them from other kinds of communications? And FW-NOT doesn't make it, you know, super easy to do that, although it would be possible. So we've talked about infrastructure as a service provider, those cloud computing models, but there's a lot more to cloud computing than just that. Can we integrate with platform as a service providers or software as a service providers? And I think that this gets more into a research question, I would say. We've demonstrated the infrastructure as a service integration possibilities, but I think going further up the stack, if you treat infrastructure as a service as kind of the most important base level and then other things built on top of that, I think the integration would become a lot harder, because then you start to require cloud providers themselves to alter their own applications in order to be able to support the SBA protocol, and that's going to be certainly a challenge. You could, however, see in some cases like the Amazon Elastic Beanstalk service, which is kind of Amazon's platform as a service offering, they power that with EC2 instances underneath the covers, which you also have control over because they are an infrastructure as a service provider as well. So in that case, you would have the ability to integrate SBA to some extent. This is a screenshot of their Elastic Beanstalk interface where you can see that the instances in that, within the Beanstalk service really are EC2 instances that you also control. But things like Dropbox, Mozy, you know, imagine Dropbox or some other software as a service provider model where you can't even see that it's listening on port 80. You can't connect to it at all until your browser itself is able to construct an SBA packet. That's probably not going to happen anytime soon. But there are other kinds of cloud computing models, like Penguin Computing's model is more geared towards high performance computing, and they also, I think, have more of an infrastructure as a service portion to their cloud, in which case SBA is probably compatible to some extent there too. There's, let's see. There are certainly, let's see, this Brian, it looks like I'm coming up on time here. There are certainly some opportunities for further research for SBA and how far it can be taken in the cloud computing environment. I think that the point of this talk was to show that from an infrastructure as a service provider model, that SBA is highly able to be integrated within those cloud provider networks. Like I said, if you choose to use FW-NOT within the Amazon AWS deployment and you have any issues with that, please just send me an email and we'll walk through it to make sure that it works. I think with that, I should close with questions. Any questions? The contact? Oh, yeah, sure. So there's a lot of these. I'd like to acknowledge real quickly, we didn't get to talk about this, but there were a couple of vulnerabilities announced in FW-NOP. I'd like to credit Fernando Arnabaldi and Eric Gomez for discovering and making that research possible. Those have been fixed since FWNOP 2.0.3. The latest release is 2.0.4, and upcoming is the HMAC SHA-256 support in FWNOP 2.5. If you like looking at software written in C and you like finding vulnerabilities, you know, this is an avenue where you can get recognition by having a CVE number assigned to a vulnerability that you may find. There have been 2 against FWNOP. I should say that they were only exploitable. One was a remotely exploitable problem in the daemon, but only if you also possessed a valid encryption key. So it's not as though it was remotely exploitable without you also knowing the encryption key to get access to the vulnerable code. And the other problem was a client-side vulnerability. But if you're interested in helping, please, it's an open source project. I would love to communicate with you if you're interested in finding additional vulnerabilities. And you had asked for contact information. Here's my email address, as well as my Twitter handle. And the slides are posted along with the demo video on my website at the links below. Any other questions? Yes? I'm sorry, I couldn't quite.
Is it running on ARM devices, such as the Raspberry Pi? ARM devices.
Oh, ARM devices, yes. I don't know the answer to that. I haven't tried it there. So if you've got one of those and would like to give it a shot, I mean, it certainly supports multiple operating systems, and it supports, you know, things like OpenWRT and things like that. And also there's an Android client too, and an iPhone client. But I don't know the answer to if it runs on ARM yet. So try it out. Let me know. Any other questions? Yes.
Do you have a list of this has been tried here on, say, Amazon? You know, this works, and these don't. Like, say, a wiki page, something along those lines.
I haven't put that together yet. He's asking for a wiki page on defining what actually works and what doesn't work within Amazon's cloud. It's a good idea. I haven't put that together yet. The closest thing are these slides, but.
Structures like, you know, there are so many different cloud providers, and not everybody uses Amazon.
Absolutely. So, you know, Rackspace and other things like that. Yeah. So the idea is to put together a wiki that says, okay, for these cloud providers, which are compatible with SBA and how, you know, perhaps with configurations listed and all of that. That's a great idea. It doesn't exist yet, but something that we could work on. Any other questions? Yes.
Any current or planned IPv6 capabilities?
Absolutely. So the question is FWNOP going to support IPv6? Absolutely. That's on the roadmap. That's, I think, in the 2.6 release, if I remember correctly. So we're going to get the HMAC SHA-256 support out first, and then I think IPv6 comes up right after that. Of course, supporting IPv6 would be done, you know, so in the IP tables world, it'll be done with IP6 tables to manipulate IP6 tables policies, and the client needs to be, of course, updated to communicate over IPv6, but that is coming, absolutely. Any other questions? Thank you very much. SPA server side, and then temporarily reconfiguring the firewall for access to whatever service is being requested. In many cases, people use it to protect SSH daemons. FWNOP started in the port knocking world. It was, at the time, it was the first implementation that combined port knocking with passive OS fingerprinting. But things have come a long way since then, and it's designed today to try to retain the benefits of port knocking, namely the default drop packet filtering stance for protected service, but at the same time solve limitations that port knocking implementations typically have, such as it's difficult to protect against replay attacks typically. You can, if you're requiring a sequence of connections to closed ports, as in most port knocking implementations do, it's very easy to DOS the port knocking server side if you're an attacker just by spoofing an additional packet into the port knocking stream, thereby convincing the server that you don't really know the proper sequence and thereby denying access to the person who's trying to gain it. SBA is designed to solve those limitations. So there are many different port knocking implementations, and there are a few SBA implementations. And the particular design goals that you, if you're looking at an SBA implementation, the particular design goals that guide the development of that project.
Warm round of applause, and go ahead and get started.
Thank you, everyone. Hello, my name is Mike Rash. Thanks for the introduction, Brian. So this is my third ShmooCon talk. I'd like to thank the ShmooCon organizers for seeing fit to have me back. The first talk was back in 2006, and the topic back then was also single packet authorization, but things have come a long way in the SPA world since that time. So I find that usually it's a good idea to give a little bit of an introduction to where SPA came from. It kind of grew up out of the port knocking world, but it is I would say quite different than port knocking generally. I found also in previous talks that it's kind of difficult to kind of leave enough time to give a really lengthy demonstration of the technology. So I'm going to try to fix that in this talk. There's a lengthy demo of integrating FWNOP with Amazon's AWS cloud service. From there, we'll try to hint at some generalized points for integration for other cloud architectures. The FWNOP 2.5 release, I was trying to finish it by ShmooCon here, couldn't quite get it done, but it's very close. This release is going to finally introduce HMAC SHA-256 support for SPA packet authentication, and talk a little bit about where SPA is headed from here. So if we're to take the trade-off of trying to deploy an SPA protective layer against services that may have problems like the ones listed here, yeah, I'll take that trade-off. My reaction to the third one on the list here, the nice, very well implemented Shodan service for regularly scanning the internet, looking for all sorts of services to be able to connect to. My reaction to seeing things like this is let's just not connect things to the internet that shouldn't be connected. PLCs that are connected into water treatment plants and connected to the power grid, probably not the best things to connect to the internet. I know it's not that simplistic, of course. People find it very useful to be able to connect to things over the network. But firewalls are all over the place too. Let's use them. So the typical port knocking, and by the way, please feel free to interrupt me at any time if you have questions. Prefer this to be a little bit more interactive, so speak up. Both port knocking and SBA have a similar workflow where you have a system that is leveraging a firewall layer of some kind, IP tables or IPFW or something, and it is passively collecting data from a user that is in possession of a port knocking or SBA client. And that client is producing a set of information which is then passively collected by the PK or the... In both the port knocking and the SPA worlds, we kind of assert that there's value in the idea of concealing a service behind a lightweight layer that is passively collecting information to be authenticated. But port knocking and SPA are quite different technologies. Neither one is designed to protect against client-side vulnerabilities. They're designed typically to protect against potential server-side vulnerabilities, and also to make services, make it infeasible to scan for services. So really what both port knocking and SPA are about is trying to make sure that services that may be vulnerable and may also include a lot more complicated code than the PK or the SPA implementations, we're trying to make sure that those services are something that you just cannot even know what to target because you cannot even scan for them. So typically we're referring to TCP-based services here, of course. UDP sockets are not required to respond with any data whatsoever, although of course many UDP servers do actually respond. So, even though neither port knocking nor SBA are designed to protect against server-side or client-side vulnerabilities, there's certainly no shortage of server-side vulnerabilities. I chose these 4 specific examples because they're all recent, so within the last 2 months or so. And if I'm asked, if I are probably going to influence whether or not you are willing to run that particular piece of software. So it's probably a good idea for me to talk a little bit about the design of the FWNOP project. So we talked about passive collection of authentication data. Currently that's done with libpcap, although I have a star there because that's going to be changing in in a future release of FWNOP with some different modes of acquiring packet data. It supports both symmetric and asymmetric ciphers, so Rheindahl for the symmetric key encryption, and it supports GPG for asymmetric encryption. Encrypted, of course, and non-replayable packets. And when I say encrypted, because FWNOP uses UDP, by default it sends a UDP packet over port 62201. Of course, the server side is never acknowledging anything whatsoever. The IP address that you want the FWNOP daemon to allow through the firewall is encrypted within the SBA packet payload. That's a very important point because any SBA implementation that does not encrypt the IP within a payload, of whether or not that payload exists somewhere in network or transport layer headers or in the application layer of whatever protocol you're using, if it doesn't encrypt the IP address within the payload, then that SBA implementation is potentially subject to a man-in-the-middle attack, where an attacker can intercept the SBA packet,